Hi, welcome back to my channel. Well, in this video I'll be doing a demonstration regarding a very important complete block design that is known as latent square design. Actually, this is a kind of a design in which the treatments are arranged into rows and columns, and the important feature in this design is the number of treatments, number of rows and number of columns are same. If we recall the conventional randomized complete block design, in that design there's an important condition that the fertility gradient must be moving only in one direction, but there are sometimes some circumstances when the fertility gradient might be moving in two directions. Then in those situations we can use this kind of a design. Actually, this latent square design, it is a kind of an arrangement of, say for example, T symbols in T square cells arranged in T rows and T columns, such that every symbol occurs precisely once in each row and once in each column. For example, if I will take an example of this arrangement, 5 by 5 latent square design, this means we have 5 treatments A, B, C, D, E, which are arranged into 5 columns, 1, 2, 3 and 4, 1, 2, 3, 4 and 5, and they are arranged into 5 rows, 1, 2, 3, 4, 5. So we have a 5 by 5 latent square design and in this design, say for example, if I will take an example of this treatment A, it occurs once in this column and once in this row. So this is actually the important feature of the design. The treatments must be arranged in such a way so that each and every treatment should occur once in that row and once in that column. If I will take an example of this C, it occurs only once in this row and once in this column. So in order to proceed, what I will do, I will write library doebioresearch in order to perform the analysis of latent square design. In our studio, I'll be utilizing this library. Then we will choose an inbuilt data of this library, lsddata. Then let us view this lsddata. So here you can see we have rows, columns, treatments, yield, two continuous variables or study variables. Here you can see we have 5 rows, 5 columns and 5 treatment A, B, C, D, E. So we have a clear evidence of 5 by 5 latent square design. So in order to proceed, what I will do, I will write the default function lsd, which gives us an output of analysis of variance along with multiple comparison test for the means. Then I will write lsddata. What is the name of the data? I will put these square brackets and I will write 4 here because I'm interested to perform the analysis of yield. If not this, if I'm interested to perform the analysis of this plant height, I will write 5 here. If I am interested to perform the analysis of both these, I'll write 4 is to 5, then comma. Then after that, what I will do, I will write it like this. I will write lsddata $sign treatment, then again lsddata $sign rows, lsddata. This is the name of the data set. Then $sign. I will write now we have done with the treatments rows. Then I will write column, then comma 1, because this symbol is used for post hoc analysis. If I will write 0, then no post hoc analysis, multiple comparison test for the means will not be done. If I will write 1, which means I'm interested to perform least significant difference. If I will write 2, this stands for Duncan's multiple range test. If 3, then it will create as an output in terms of Tukey's HSD. So I am interested here to perform only the post-hoc analysis in terms of least significant difference or the traditional critical difference. Then I will press on this enter. So we have the results here. You can see in this case I have performed the analysis of both these variables, the yield as well as plant height. As far as yield is concerned, the treatments are found out to be significant, but rows and columns, these treatments are significant, but rows and columns they are not significant. But if I will take an example of this analysis of variance as far as this source of variation is concerned. We have equal degrees of freedom for rows, columns, and treatment, because of the reason that we have the rows, treatments, and columns are equal in number in case of latent square design, because it is here t minus 1, d minus 1, and d minus 1. So 5 minus 1 is 4, and here it is t minus 1 into t minus 2, the residual error degrees of freedom, we can say it's 12. It's 5 minus 1 into 5 minus 2, that is 4 into 3, that is 12. So here you can see, as far as this normality test is concerned, it is found out to be non-significant, which gives us an indication that the errors are normally distributed. Then after that, once we are done with the normality test, appearability test, then we can find out whether our treatments are significant or not. But before that, we have in output the standard error of mean and standard error of difference of mean, which are very much required to calculate latent square this least significant difference. Then we have mean square error for the model, then the degrees of freedom for error, then general mean, coefficient of variance, and variation. Then we have t value, which is very important to calculate this. In this case, B and C treatment are non-significant, B, C, and D are non-significant with each other, but they are significant if we take the example of E and A. The thumb rule is, if the difference between two means is if the value of the difference between two means is greater than this standard critical difference or least significant difference, then they are found out to be significant. But in this case, B and C, the difference among them is low in comparison to this standard latent square design, and same is the evident from these codes. They are given the same code because their difference is very less in comparison to this. That is why they are non-significant. As for the plant height is concerned, only rows are found out to be significant, but the errors are normally distributed by means of Shapiro-Wilk test, and all these values are non-significant here, because the LSD value is 5.3, which is too much higher in comparison to the difference among these treatments. So taking into consideration of this library, we can perform the analysis of latent square design if our treatments are arranged into rows and columns like this. So this library is very helpful. Hope you will like this video. Thank you very much.